Distributed loads we have two learning objectives here. We need to be able to resolve these three shapes, rectangle, triangle, or trapezoidal distributed load into concentrated forces. So we're going to take a distributed load and we're going to turn it into a concentrated force, which is like a point load. And then we're going to use the stuff we've been talking about, the centroids of areas, to resolve a distributed load described by a nonlinear function into a concentrated force at the correct location. So we're really doing stuff that's very similar to our centroids of areas by integration. And so for us to understand what is this distributed load, well, I took some Jenga blocks here and I stacked them on this really flexible ruler. So there's just this down here at the bottom here, there's just this like really flexible ruler that's just sitting underneath all these Jenga blocks, and they're 3 blocks high, right? They're 3 blocks high, and they're also 3 blocks deep. So that's into the picture there. And so what we're doing with the distributed load is we're going to simplify this. And so instead of having like all these Jenga blocks just spread out over it, what if I took all those Jenga blocks and I moved them all to the same line? So wouldn't that be equivalent to if I took, like, I was 3 blocks deep? Well, what if I took those 3 blocks deep and I just stacked them on top of each other? And so I'm at 9 blocks right there. And so where is the line of action of that resultant force? Won't it go through the centroid of that area? And so where's the centroid? This is basically a rectangle, isn't it? And so the centroid of the area would be halfway from left to right, halfway from top to bottom. And so the line of action would go there. So actually we could replace our original, all these Jenga blocks, with just one force, right, acting in the middle right there. And so now let's resolve that into one force at one location. How many blocks and where? Oh, let me call on somebody in the front row, Daniel Thorne. How many blocks would I have to replace that with?
Sorry, can you repeat the question?
Yeah, how many blocks? If I wanted to resolve it into one force, so if I have my Jenga blocks, how many blocks would I need?
Would you just like compile them all into like just one big block?
Yeah, absolutely, right? I would just take them, and then where would I put them? I would put them at the centroid, right? Yeah, absolutely. So yeah, we take all those blocks, and we have 6 stacks of them, so we put 54 blocks at the center of that area right there. And I started stacking Jenga, and I got like 9 high or something, and then they started falling over, and I was like, oh, wait a second, I have a better idea. I could just take all 54 of those and put them in the Jenga box, or the Jenga container there. And so yeah, we've got 54 blocks that are acting right there. So that's what we're trying to do with these distributed loads. We'll start with a distributed load, and we need to take it down to a force and know where that force is acting. But I also want to talk about, these are equivalent, but what does that mean? What does equivalency mean? And we talked about equivalent systems before. Are the support reactions the same? And so that would be, if we have our original system over here, and then this would be an equivalent system, the support reaction would be how much force is holding up right here, is holding up each side of those. Would that be the same if I had my original versus my equivalent? What does everybody think? Go ahead and throw it in the chat. Yes or no? Are the support reactions the same? Okay, I see a no. I see a yes. What does everybody think? Okay, now I'm seeing yeses. Another yes, another yes. Yes, the support reactions are the same. Yes, absolutely. That's what it means to be equivalent, is that the support reactions are the same. So this has to be the same as that, because isn't it the same amount of blocks, and it's at the centroid of all those blocks? So the support reactions have to be the same. Now, how about the deflected shape? And it's really hard to see in this one, with the deflected shapes, but actually the deflected shape is no. Those are going to be different. So while our support reactions are the same, the internal stuff, the internal stuff is what causes that deflected shape. That is going to be different. Okay, so that's what equivalency means. Support reactions are the same, but the deflected shape is going to be different. And we'll continue talking about that kind of stuff this semester. Okay, now I'm showing a picture of somewhere on campus. Does anybody know where this is a building, one of our newer buildings under construction? Can anybody figure out where that, or what building is that on campus there? I know, how about, no, it's not the parking garage. Leah, what do you think? Leah Walker. Any ideas where that is?
Is that Spruce?
It's not Spruce. It's older than that. It probably was finished when many of you started at Mines. Actually, I think it was finished. But it's a newer building. What's another newer building? And look at the background. What do you see in the background? What's like back here? Yeah, Coors. I see Lilia got it. It's Coors Tech. Yeah, this is actually Coors Tech. And I'm showing this picture. This is, I would stop by and I'd stop by after class and like watch the construction occur. And Scott Strong would come by and just be like, dude, what are you doing? And I'd be like, oh, I'd be telling him about like everything that's going on. And he's just like, oh, wow, this is really cool. Now I see why you're just sitting here and watching this. And they were bringing these beams in here for the iron workers, they actually clipped a piece of the of this elevator shaft over here, and like a little piece of concrete came off. But I think everything's okay. Like I think it's fine. It's probably safe. More than likely, it's probably safe. So. No, but actually every single beam in this building was designed with a distributed load. So these distributed loads are very relevant to practice. And so they figure out the distributed load based on the pressure that's exerted over the floors. And so this would be like on the west side there, and these are like, there's doors right here that you walk into, and you walk down that whole corridor. Well, every single beam that you're walking on is designed for a distributed load. Also, I'm showing this camera because I'm pretty sure, so see, that's the problem with like somebody observing construction site, is you see all these like things happen, like they hit the elevator, tower, and concrete comes flying off. And then you see somebody welding on a ladder that's not harnessed in. I'm pretty sure that's a OSHA violation right there. Okay, so yeah, every single beam in here designed, and look at all those beams. So the beams are these horizontal, the rusty steel, all this stuff going, look at every single one of those designed with a distributed load. Okay, so now what is that? Yeah, Cody knows anything over 6 feet without a harness, right? Yeah, is an OSHA violation. So what is this going to look like in one of our textbook problems, right? It's going to look more like this right here. And so what we're going to do, just like we did with the Jenga blocks, is if we can find the centroid of that area, then we know where the equivalent force would act. And if we can find the area, then we can figure out what the force is equal to. And so our problems are going to look like this. Here's homework problem number 1. We use W to describe distributed loads. I don't know why we use W for a distributed load, but that's just the common letter we use for distributed loads. And in this one, they want us to find what is the resultant force and where is it located. So we'll look at that, problems like that. Replace this with a force and a couple moment at point O. So if we can figure out, okay, well, what's this triangle doing? What's this triangle doing? Then we can figure out a concentrated force, and then we'll use our equivalency things to figure out what that couple moment is. And then the third homework problem here is a trapezoid. So what is the resultant force and where is it located? So those are the types of problems that we're going to be looking at. Well, let's jump in and let's draw some pictures on these distributed loads. And I want to start by relating this to something that we're probably a little bit familiar with. What if we had a board here? And so I've got this board, and so let's say I've got a board here. Okay, so here's the board I'm drawing. And so let's say I left this outside. I leave this board outside and it snows. And maybe later this week we're gonna get like a bunch of snow. Actually, I don't know if we're supposed to get a bunch of snow later this week or not. So let's draw a picture of this board here. And it goes back into the page a little bit. And then we're showing kind of like an isometric view of that board there. Well, let's say we get all that snow, right? And so we have all this snow that's going to pile up on top of this board here. And actually in the golden area, The snow load in around Golden, for like, if you looked up in the building codes, we're looking at about 40 pounds per square foot is a typical snow load in the Golden area. Jefferson County is one of the few counties in the whole world where you have to look up your, or at least in the whole US, where you have to look up your snow load based on your address, because you can't just say like for Golden, right? Because if you go up North Table, or not North Table, but if you go up Lookout Mountain, if you go up towards Genesee, don't you think they get a lot more snow up there than we typically get down here? So you might be finding like 60 pounds per square foot. 40 pounds per square foot, just to give you an idea of what that would represent in terms of snow, that would be equivalent to about 9 inches of water. So 40 pounds per square foot, that'd be like taking, it's almost like making a swimming pool out of your roof. So it's a lot, right? We can get, we can get 4 feet, we can get 5 feet of snow here. So imagine having 9 inches of water. Like, water's heavy, right? So the 40 pounds per square foot is about 9 inches of water. But let's just say that this is our snow load here. And we have this board. I'm going to make the dimensions of this board, actually, I'm going to make it a 2, what is that? That's a 2 by 8, I think. And so actually, let's make this dimension right here 0.75 feet. And then let's say our board is pretty long. Let's say it goes back 10 feet into the page here. Well, this is our 3D representation, right? In 3D, this is what we have. Now, in 2D, though, we can look at this thing along the length. And so what if I had that board there and we looked at it from this angle, where this is our 10-foot length right here, or L equal to 10 feet, then this is what's going to be actually our distributed load. And so to get that, wouldn't we take that snow, and just like we did with the Jenga blocks, wouldn't we take that snow and we're just going to basically squeeze it all together to where it's only acting right down the center line of the board, right? So we're going to take it, we're going to squeeze all that snow to where it's only acting along the center line of that board right there. I'll put some more arrows in here. And actually, when we draw our distributed loads, it does not matter how many arrows we put in there. All right, that doesn't matter. The length of the arrows, though, is still representative of the magnitude of that distributed load, W. So W is our distributed load. And so if we have our snow in 2D, and so we still have our snow load on here, we still have this snow equal to 40 pounds per square foot. But what would it be? What would our W be for this one? If we think about the Jenga blocks, right? What did we have to do? Which dimension do we have to multiply out? Which dimension did we take out of this? And let me ask somebody in our front row here. How about Robert Warkentine? Is Robert here? I don't know if Robert is here.
I'm not sure.
Oh, you're here? Okay. All right. Well, what do you think? What dimension did we take out? When we changed from 3D to 2D, Robert, what dimension is gone now?
The 0.75 feet.
Yeah, the 0.75. So actually, we can find our W by taking our 40 pounds per square foot times 0.75 feet. And look what we're going to end up with. We're going to end up with 30 pounds per foot. So a distributed load is always going to be in like per foot or per meter. And so what that distributed load is saying is that it's continuous, right? And so for every foot along that, we have 30 pounds. So that pound, so these are always the units for W. It is always going to be like a pounds per foot. It could also be like a kilonewton per meter. It could, right, it's always going to be per some length on those units for our W. Okay, now this is actually where we would start on our homework. We would be given W when we're starting our homework. This whole thing with bringing in the pounds per foot squared, that's a pressure. And so we're not going to see that on our homework. We're just going to see this W, but I want you all to understand where that W comes from, because if I just give you, oh, W is just in pounds per foot, it really doesn't make a whole lot of sense there. So now, what is this equivalent to? Wouldn't this be equivalent to, if we have our beam here, our board, and we have this L of 10 feet. We know we have a W, and I'm going to draw this, just the outline of it. We know that this right here is W equal to 30 pounds per foot. Well, we can find the equivalent resultant force is going to be at the centroid of that. And let me just call it FR. And so FR, that distance right there, is going to be L over 2, or 5 feet. So FR is just equal to the area under the distributed load, W. And so for a rectangle, it's just going to be the base times the height, 10 feet, times 30 pounds per foot. And so we're going to end up with 300 pounds. Which, isn't that also the total weight of the snow that's sitting on top of that board? So it's really, these problems are very much related to our centroids of areas that we've done, where we are just looking for the total area, and then the location of the centroid of the area is where the resultant force is going to occur. Now, the advantage of getting this into 300 pounds is that now we can take moments. And so if we were designing all those beams in Coors Tech, we would need to know what the resultant force is, so that we could say, okay, well, let's take the moment and let's figure out how much bending is occurring. And let's figure out, then we can start designing this thing to withstand those bending forces in there. What about a triangular? Let's keep moving here. Actually, let me see if does anybody have any questions? I kind of lost track of the chat there. Okay, it looks like I'm all caught up on the chat. Any questions? Okay, let's take a look now. How about a triangular distributed load? So we looked in our learning objectives. It said that we needed to be able to handle rectangular, triangular, and trapezoidal. So a triangular distributed load. So let's say we have let's take our same board. And so we still have this, my board was sagging down right there. So we still have this L is equal to 10 feet across here. And let's say now we, and I'm sure some of you all have been heading up skiing, but let's say now we we pile the snow up so it looks something like this. And so we have 0 snow over here at this spot. Really, our W is going to be equal to 0 pounds per foot right there. And let's say over here on this side, we pile it up so that W, we can call this one a W1, call this one over here W2, and W2, let's say we get to 100 pounds per foot. over here on this side. And I can draw some more arrows in here, but remember, it doesn't matter how many arrows we draw. Anytime we have a distributed load, it's a continuous load. Think about the snow or the Jenga blocks, right, where it's going across that whole thing, but it's telling us in each foot how many pounds per foot do we have. So technically, right, it's changing this whole way, where, like, you know, right here maybe it's at 90 and then it's at 80 and then all the way back down to 0. But we can find our FR, and so we can find the magnitude and the location by just taking the area of this. So FR is still going to be just the area under W, which will be 1/2 times 10 feet times 100 pounds per foot. And we see the units on there, they're working out, aren't they, right? The feet cancel out, and so we're going to end up with 1,000 divided by 2. So we end up, we took a little bit more snow than we did before, right, to make our ramp here. And so we've got 500 pounds. And then where does it act? It acts at the centroid of the triangle. And so we would draw this up here. Where's the centroid of our triangle? About right there, right? It's 1/3 from the bigger side. And remember, this is the line of action goes through that centroid, but I'm showing the force actually acting on the board, right? Because isn't that force going to be, it's still going to be acting on the board there. So there's our FR, and then this distance right here, that would be 1/3 times that 10 feet. So now, again, we can do stuff like take moments, and we can, you know, for design. And so we can't do that with just a W. If we have a W, it's really, it's acting over the whole thing, so we can't really take a moment with W. We have to convert it into an equivalent resultant force, into a concentrated force, and then we know where the force is located. We can take moments and do things like that. Now, how about for the third kind that we can see, a trapezoid? Trapezoidal distributed load. Let's take our same board here. Okay, and I see a question in here about the last one. Why do we multiply the FR for a triangle by half and not by 1/3? Well, I'm not taking the moment necessarily yet. I am just, I'm finding the area of the triangle, right? So this area under W, this is really, that's the area of the triangle. And so I could see how that would be confusing, right? It's like I've got a 1/3. Well, I'm not taking the moment yet. I'm just finding the area of the triangle, so 1/2 the base times the height. Okay, now a trapezoid we have here, let's say on this side over here, how about let's make W1 equal to 25 pounds per foot. So we got 25 pounds per foot right there. And then over here on this side, what if we have 75? Well, that's a 2 again. 75 pounds per foot. Now we've talked before, and I'm just going to draw the outline this time. I'm not even going to draw any additional arrows in between, although there will be additional arrows in between here. But we've talked about before how we only need to memorize the centroid of 2 shapes. We need to memorize for a rectangle and a triangle. So how could we do this? We don't know where the centroid of a trapezoid is, but what could we do in order to still be able to only use those 2 things and still find this? Anyone? Yeah, triangle, split it into 2 shapes. Absolutely, right? So yeah, let's take this, and let's break this up into a rectangle and a triangle because we know, okay, well, the rectangle, we can find the area of the rectangle, and that's going to be an FR, let's call that FR1, and it would be halfway. Oh, I forgot to draw my L down here. Actually, we'll draw L in a little bit. Let's leave it off. It'll give us more room to draw some other things. So yeah, we're going to have this, we'll call this FR1 right here. So there's our FR1, and that'll be for the rectangle. And then the triangle, at the centroid of that triangle, that's where we're going to have our FR2. And so let's see, we know for the rectangle part, right, this should be exactly 5 feet right there. And then another 5 feet right there. And then for FR2, again, that's going to be at that 1/3 of the whole distance of 10 feet right there. And so concepts are exactly the same. FR1 is going to be the area of the rectangle, and FR2 is going to be, actually, let's not write FR2 yet. Let's go ahead and do the area of the rectangle. So let's see, the area of the rectangle is going to be 10 feet times what's the height? The height of the rectangle is 25 pounds per foot. So we're going to have 250 pounds. Now, FR2 is going to be the area of the triangle. And so this will be 1/2 times 10 feet. And then the height of that thing, what is the height of that thing right there? How about Lizzie? I'm not sure exactly how to say your last name. Is it Wheel?
It's Weil, yeah.
Weil, thank you, Lizzie.
No worries. So at that point, yeah, I agree with what they're saying in the chat, 50.
Yes, absolutely, right? Yeah, 50 pounds per foot. So it's not 75 because we've already cut off the rectangular part, right? And so yeah, 50 pounds per foot, absolutely. And so that would be like this distance right here is what we're looking for with that triangle. That's our 50 pounds per foot right there. And so we're going to end up with, let's see, another 250 pounds. Okay, any questions? All right, so we've covered a rectangle, a triangle, and a trapezoid. Let's jump into and let's look at how we could handle all this stuff in a problem similar to the homework. So let's say we have a beam here, and
sorry,
acting
I do have a
on
question really quick.
Oh yeah, what's up?
So just for the resultant force, we're just adding the two forces together to find the total load, or?
Oh, great question. Yes. Okay, so yeah, FR total would be equal to FR1 plus FR2. And where is that going to act?
Like the average distance between the two?
Yeah, or based on the weighted average, right? If they're both 250, then we could just, it would be like right in the middle. But yeah, we're going to take the weighted average, and actually we'll go through that process on this problem in more detail. But that's a great question, Colin. Thank you for asking that. I want to point out another thing too. If you're not asked to find the total resultant force, you don't have to. Because if I know that I have 250 at 5 feet and the other 250 at 1/3 from that right side there, I can take moments and I can do all my analysis from there. I'm good to go at that spot. But on some problems, like in this one, this next one that we're about to do, they ask us for the resultant force and where is it located. Okay, so we'll do that part in this one. And for this problem, what we have is it looks like this. There's a triangle and then there's a rectangular. segment of that right there. And so we're going to have our W right here. I'll draw a few arrows going down in here just so we are clear. So our W is equal to 60 pounds per foot, and that's that W on this side over here. And they tell us a couple of dimensions. And so there's actually this beam, and I'm going to draw a support on here. So this beam is actually, this is called a pin support, and we're going to talk more about this on Wednesday. But this pin this is how it's connected to the rest of the world. And then over here, this is what's called a roller support, and we're going to talk about this. But I just wanted to throw it in here since we're doing this to say, well, this board is supported. All right, so we'll talk more about those supports next time. But it is supported. It's not going to fall down or anything. And so they tell us that this distance right here is 10 feet. And then the distance to this last part is 5 feet. And what they want us to find for this problem is FR. And where is it located? Measured from A. And so we'll put A over here on the left, and then we'll call this point over here B on the right there. Okay, so for our solution, I think we should know that we just need to find, we're going to have a triangle, we're going to have a rectangle, and we can find the FR from those two shapes by just taking the area of those two shapes, and they're going to occur at the centroids there. So let's take point A right there. I'll do point B right here. We've got I'm just going to draw the outline of this and say, and really, because all I really care about is what the shape looks like, right? I know this over here is 60 pounds per foot, and we know that we have a distance here of 10 feet and this distance here of 5 feet. And so we would have our FR for this shape right there. There's the centroid of that one right there. That would be, we can call that one FR. Let's see, what did I call it in my work here? I didn't even call it anything. We can call that, let's call that FR1. And then at the centroid of the triangle, we'll have our FR2. And so FR1 is just going to be 60 pounds per foot times 5 feet. And so that's going to be 300 pounds. And then FR2 will be 1/2 times 10 feet times, again, 60 pounds per foot, because that 60 pounds per foot is the height of the triangle. And so, oh wow, we have another 300. Is that right? 300 pounds. Oh, I see. I wrote down, that 5 foot should have been 6 feet. So our numbers are a little bit different there, but that's totally fine. Okay, so we have 300 pounds and we have another 300 pounds. We know where these are located, right? Let's specify our locations here. So if we want to measure things from point A right there, well, we know that distance right there. What is that distance going to be? Anyone? Yeah, 2/3 of 10, 6.66. Right, absolutely. 2/3 times that 10 feet right there. And then how about the distance all the way out to our FR1 right there, because we're measuring everything from A, right? So if we go all the way out there, then isn't that distance is going to be 12.5 feet. So we have our 2/3 of 10, we have our 12.5 feet. And so our final system that we're looking for here they want us to find FR, and where is it located? Well, if we have our beam, we want to know, here's our FR, which is going to be just equal to FR1 plus FR2. And we want to know, well, where is that located? What is that distance X? Right there. So we go back to figure that out. We are going to go back to this idea of equivalency. So we're going to use equivalency to do this. And so don't we know that FR1 times that 12.5 plus FR2 times 2/3 of 10 feet is going to have to be equal to, if we're doing this in terms of equivalency, FR times X. And I see some questions in here about the 2/3. Yeah, right. Be careful with the triangles. The centroid from that smaller side of the triangle is 2/3. From the larger side of the triangle is 1/3. So I'll draw where the 1/3, do it in green right here, right? That distance right there would be 1/3 of 10 feet. But since we want to know where everything is relative to point A over here, which is right there, then we need to, nope, I didn't need to go there. Then we need to make sure that we're using the correct, is it 2/3 or is it the 1/3? And I don't think it's a duh kind of thing. I think, right, we gotta, any of those little questions, if you had that question, I'm sure somebody else had that question. So thank you for asking. Okay, any questions on this equation, right? We're using equivalency, right? These are the moments, like these ones right here. This is really the moment about A from that, our first picture, our first pick in the solution that we're showing. So that's from this one, right? We're using the FR1 and the FR2. And then this one, this is the moment about A from the final system. And so we're setting the moments equal to each other, aren't we? And it's basically, it gives us the weighted average. And so we can find X is going to be equal to FR1 times 12.5 plus FR2 times 2/3 of 10. Times 10 feet. And then we would divide that by FR1 plus FR2. And so we're going to end up with X is going to be 300 times 12.5 plus 300 times 6.67 divided by 300 plus 300. And so if anybody else has their calculator, I meant to make that distance originally different. So I need to plug in some values here. 300 times, if somebody wants to check me or beat me to it, times 12.5 plus 300 times 6.67 divided by 600. And we end up at I get 9.585. Oh, there we go. Ahmed beat me to it. So 9.585 feet, which if those are both 300, then isn't that smack dab in the middle, because the weighted average of those two would be right in between 12.5 and 6.67. So isn't that the same as just taking the average of 12.5 and 6.67, because the 300s, the two forces are exactly the same. Okay, so that should give you all the tools that you need to tackle those homework problems. I think typically these are kind of on the easier side for our homework. So hopefully you find them that way as well. Let me go back as soon as I know everybody is done writing this stuff down. Let me go back to the pictures of those homework problems and we'll just take a look at that. Okay, so, right, how about this one? That seems pretty straightforward now, right? Resultant force and where? Well, we got a rectangle and a triangle. We can break it up, find the resultant force. This one, a little bit more involved. They give us the triangles. Now we know that they're telling us to replace it with a force and a couple moment at O. Now, what did we do in our example today? We just found where that FR is located, but if we're replacing it with a couple moment at O, basically what they're doing is they're telling us where to put our force. So we'd still do the same thing. We have an F1R, an F2R right there, and then we're still going to apply those same rules for equivalency. So we do have to go back and review those equivalency things, but we still have those same two rules for equivalency for this problem. And the two rules are that the forces can't change, right? Equivalency. So the forces can't change. If we have a FR1 and an FR2, well, we can figure out what the net force is applied. But then we want to find what moment do we have to apply right here so that we created the same moment of the original system. So we're still going to go moment at O of the original system has to be equal to the moment about O of the equivalent system. So we're still creating that same idea there on that one. And then number one, very similar to the problem that we did today, just flipped around a little bit, where we're asked to find the resultant force and where for this one. Oh, and here's those supports, right? This is a pin support, a roller support. We are just worrying about the applied loads. We don't have to worry about any of that stuff. We'll get to that stuff on Wednesday, actually. So if you have any questions, I will stick around for a couple of minutes. Also have office hours at 3 o'clock today. You all have a great rest of your Monday, and we'll see you on Wednesday.